Hello, this is Jennifer Dassinger with A Plus College Ready, and I'm here today with you on Unit 5. This is our second PowerPoint presentation on bonding and molecular geometry. Covalent bonds. Remember from our last video, we talked about the three types of bonds are ionic, covalent, and metallic. And I told you that we're going to spend a lot more time on covalent bonds. Well, this video and the next screencast video are all about covalent bonds. And we know the definition of a covalent bond is that mutual attraction by the nuclei. So it's not really going to be 50-50. Most things usually aren't. So the electrons are going to repel each other and the nuclei are going to repel each other within a covalently bonded compound or molecule. They're going to reach that distance, and that distance with the lowest possible energy will create its bond length. Now remember, Coulomb's law. This is that application. The electrons are going to repel, the nuclei are going to repel. Remember, the proton to proton will repel each other. However, there will be that point where there will be that attractive force of the outside of electrons to the protons of one atom to another, and that's where that bond length will be from one of the radius between the two nuclei. So there's several things going on. The attractions of the electrons to the protons in the nuclei, the repulsion of the electrons within each atom and with the other atom, and the repulsions that are occurring within the protons of the two atoms in the molecule. So let's look at hydrogen, for example. If you notice the radius at the top of 45, is that at the highest? No. The highest potential energy that we see is the 45, but the lowest, the observed bond distance, the radius is 74. So if you notice, where does it really want to be? It wants to be at the lowest possible energy. And where are we going to see that? Not at the 300 radius difference, not at the 150. 74 is squishing it too close together, and then it bounces back up and it's at its lowest possible energy state. And that's the 45 radius that you're going to see there. So remember, bond length is the distance between two nuclei where the energy is minimum between those two nuclei. Okay, remember, always lower energy state. So a covalent compound or molecule is where those two electrons are mutually attracted. So why should they attract? Well, octet rule, right? They want to, quote, look like the noble gases, but more importantly, they want to be at that lowest energy level. And again, that's our answer that we use. Not that they want to be like noble gases, but that they want to be at the lowest energy level. So if you notice, the two fluorines are representative of a diatomic molecule. And don't forget, you have the 7 diatomic molecules. My little phrase is Brinkel-Hoff. Again, bromine, iodine, chlorine, nitrogen, hydrogen, oxygen, and fluorine. They actually make a 7 on the periodic table. So take a look, pause the video, and highlight the periodic table of those 7 diatomic molecules that bond to each other in nature, and they'll be found there. So notice they create a singly covalent bond. So they share those electrons. Now, notice on the PowerPoint it has lone pairs. In your writing, in your FRQ writing and explanation, we don't want to use the phrase lone pair. I know, I used it for years. It's not the best phrase. The best phrase is going to be unbonded or unshared paired of electrons because they have the potential to be paired. So let's take that out of our vocabulary and keep the lone to Lone Ranger. No pun intended. Moving on. Now let's look at our Lewis structure of water. So we saw fluorine had the lowest potential energy, and it's a diatomic molecule, and it was bonded to itself. By definition, that fluorine was nonpolar. But if we look at water, and we look at that it creates this single bond of the hydrogen on either side. And remember, hydrogen is partially positive and oxygen is going to be partially negative. So if you notice those overlapping there, and realistically to the right, that's not the best Lewis diagram, but we're going to practice those in a little bit. So it'll create a single bond of the hydrogen to the central atom of oxygen on either side. So what is a double bond? A double bond is two atoms that share two pairs of electrons on either side. So if you notice, carbon dioxide is actually going to create this linear structure, and it's going to have double bonds. Notice 8, 8, and 8. Carbon's happy. It only gets 8 electrons. But look back up at that hydrogen. Did hydrogen go to the octet rule? No. Hydrogen is an exception of the octet rule. Remember, its maximum amount of electrons that it can contain is 2. It's one of the exceptions. We'll look at some more, but hydrogen is one of the exceptions. Now notice at our double bond, oxygen has 8 and carbon has 8. Therefore, that is the best Lewis structure, the overlapping of two pairs of electrons. Okay, now let's look at our triple bond. Our triple bond has two atoms that actually share 3 pairs of electrons. Notice nitrogen has 8 electrons and the other nitrogen has 8 electrons. Remember, nitrogen is part of that 7 diatomic molecules, part of that Brinkelhoff. Remember, Brinkelhoff. And if you notice, it creates those 3 shared pairs of electrons, and everybody's happy. Happy. And it's non-polar. So if you notice the bond length, bond energy is tied to bond length. And if you notice in the chart, as you increase in energy, you're going to do what? Well, if you notice, a double bond length of 121 for carbon to oxygen is less than the bond length than carbon to oxygen, The double bond in carbon dioxide is less than a singly bonded carbon to oxygen. Now that's the bond length. What do you think that has to do with energy? Well, as the bond length decreases, the energy is going to increase. Remember, the more layers of rocks that you have on a wall to try to kick them down, it's going to be harder. If you had 1 layer, pretty simple. 2 layers, harder. 3 layers, more challenging. Think about it as a kid in elementary school when you played Red Rover. Hopefully you got to do that. And if you chose the weakest length that you saw on the arms in Red Rover, you didn't take somebody who doubled up or got closer to each other and their arms overlapping, because you knew that would take more energy to break that bond. So therefore, if you notice the bond length, triple bond has the shortest, double bond is the middle, and single bond is the longest bond length that you're going to have. So what does that mean? Polar and nonpolar. Well, let's take our classic example of hydrofluoric acid, or HF. And a polar molecule means that the electron density is unequally distributed. So if you notice, hydrogen is electron poor and fluorine is electron rich. Therefore, it's got 3 sets of unshared pairs around the fluorine. It's going to be pulling that hydrogen along, as I show you in this PowerPoint right here. So there's that electron rich, there's that electron poor. So this is very polar. Partially negative on the fluorine and partially positive on the hydrogen. Let's take electronegativity. We've discussed this before with ionic bonds in terms that it has electronegativity of 1.6. Well, covalent, has less than 1.6 electronegativity. And if you notice, the ability to attract electrons is electronegativity. Electron affinity, notice, and electron negativity. It's relative. It's all relative. So affinity is measurable. Electronegativity is, well, it's relative. And we know that fluorine has the highest electronegative value of 4.0. Chlorine has a 3.0. Let's look at this chart. I'll demonstrate. So as you look at the atomic numbers and you go across the periodic table, hydrogen has electronegativity of 2. Look at fluorine, has electronegativity of 4. Chlorine has 3. Bromine has just shy of 3. And iodine has little less than bromine. So obviously the halides, fluorine, chlorine, bromine, and iodine, have the highest electronegativity. Notice family 1 metals, the alkali metals, have potentially the lowest electronegativity values. Here's another way to look at it. If I were to look at the bond electronegativity difference and calculated those values, that will tell me that it is truly ionic or covalent. And then it'll even tell me if it is nonpolar covalent or polar covalent. So if you were to calculate your electronegativity differences and saw that 0 to 0.04 is nonpolar, and anything 1.6 is greater is ionic. Now there's that gray area there, but potentially if it's a metal to a metal, you're still going to have an ionic, okay? And 0.5 to 1.9 is polar covalent. So we got to classify things as polar covalent, ionic, or nonpolar covalent. So if we take cesium chloride, we take the electronegativity difference, it is ionic. And of course we know cesium is on the left and chlorine's on the right. If we look at water and take the electronegativity difference of that, hydrogen and oxygen, 1.4, polar covalent. Then if we take this, whatever this thing is, H2NNH2, we really don't care because on the AP exam they're going to give you something weird. I don't care what it's called, but I can look at my electronegativity differences and I can tell you that it's going to be a non-polar covalent. So don't forget, if they give you something funky, you can still use your information to solve for the problem. Writing Lewis structures. When you draw a Lewis structure, here's some simple set of rules, okay? Take a moment, pause the video, and look at these set of rules. Now that you've looked at the 4 basic rules, let's look at the key parts. In 1, the major important thing is to put the least electronegative element as the central atom. Atoms with greater electronegativity are terminal atoms, except for, of course, hydrogen. Hydrogen only has 1 electron, so therefore it has to be a terminal atom, and that's in 3. So we're always looking at the octet, completing that octet. Notice in number 2, count the total number of valence electrons. Add 1 for each negative charge, so if it's a polyatomic ion, such as a carbonate, it's going to have a negative 2. It's going to have 2 additional electrons. If it's something like ammonium, NH4 positive, you're going to subtract 1 electron because of that positive charge. Now look at number 4. If the structure contains too many electrons, when in doubt, double it or triple it. Now our next video will go into great detail as to how to draw our Lewis structures. So stay tuned and we're going to practice drawing our Lewis structures for part 2 of our chemical bonding.